One of the things that I was emphasizing, was in the basic way that the event list works is that events get scheduled. They're kept in order of scheduled time, not the time that they were scheduled, but the time they're scheduled to occur. And hopefully that hand simulation that I tortured you with gave you at least some sense of what that's like. In other words, the events do not occur in the order that they are, that they get scheduled. They occur in the order at which they are scheduled. And in the basic form, the only way that an event comes off the event list is if it bubbles up to the surface and the event list says, okay, you're next. That's the only way that events are coming off. But there's another way we can cancel events, and that is using something called a canceling edge. And I'll show you how that works. And in some of the subsequent models that we'll encounter, we'll see where that comes into play. One way to kind of think about this, at least in a somewhat abstract sense, is if you remember, we maybe imagine an event that a missile gets launched, and that would schedule an event sometime later that the missile impacts. However, consider a scenario in which there's some kind of defensive mechanism against the missile. In other words, the missile could be intercepted and destroyed before it actually impacts. That's, depending on which side you're on, that's something that is a happy occurrence or a not so happy occurrence. So the thing is that when, at the time the missile is launched, you don't know anything about the countermeasures, and you don't know whether they're going to be successful. And then sometime later, there are other events that might get triggered that would cause the missile to be intercepted. So when that happens, let's say that the intercept of the missile was successful, the event list doesn't know anything about that. In other words, that impact event that was scheduled when it was first launched is still on the event list. And so even though the missile was in the model was intercepted, that impact event is still on the event list. And if you don't do something about that, you will have destroyed the missile, and yet the missile will still have hit its target. And that's not what you want to do. So there are basically two possibilities for that. One is you could have a state variable that says, oh, by the way, this missile was destroyed before it impacted. And then when the impact event occurs, you don't do what the normal state transitions for that impact would be based upon the fact that it had previously been destroyed. The thing is that aesthetically, that's not ideal, because really that impact event shouldn't happen at all. And that's where a canceling edge comes in. So a canceling edge is the inverse of a scheduling edge. And what it does is it's going to take an event off the event list. Then the second event graph item extension that we're going to talk about is having parameters on edges, and which are going to feed into arguments on events. And then we'll see some examples for all of this. So let's look at a canceling edge. Again, this is also in the reading. And I seem to vacillate between having two L's and one L in canceling. I'm not sure exactly which one is correct, but this is how it basically looks. And let's say I like a red color here. All right. So remember, for a scheduling edge, this line is solid. A canceling edge has a dotted line. But again, it connects two events. And the idea here, we have event A, again, that corresponds to a state transition. And here we have an event B, and that corresponds to another state transition. So the idea is that B had previously been scheduled by some other event. Otherwise, this doesn't make sense. But this is just the canonical form. The way that it works is when event A occurs, again, as with a scheduling edge, we have a Boolean condition which is either true or false. But if it's true, then what happens is the earliest occurrence of a previously scheduled event B, in this case, the event that it's pointing to, is simply removed from the event list. So in this particular case, if event, or the example I was mentioning before, if event A is that event A might represent a successful intercept of the missile, and then if B were the impact event, the Boolean would be the Boolean I would be the intercept was successful. And so the way to read this would be, if the intercept was successful, then the impact event is removed from the event list. In other words, it doesn't happen. Okay, so that's how a canceling edge works. So here's a simple example of what we might do with this. Now remember our arrival process, and the arrival process in its basic form simply runs forever. And if we don't stop it, then it just keeps going and going and going. The way we stopped it in your computer assignment was you told the event list, stop at this time. So that's the way that it's done. There may be circumstances in which we want to stop the arrivals, but not stop the whole simulation. Here's an example of this. Supposing that we're modeling a store that opens at 9 in the morning and, let's say, closes at 7 in the evening. Now, when it closes, then it basically, you imagine some guy at the door. So he kind of locks the door and prevents any new customers from coming in because, sorry, we're closed. What happens to the customers that are inside the store when it closes? Well, if you just kind of stop the simulation, then you've sort of left all those customers in the store. What if you wanted to instead model what happens in the actual store, which is you put the sign that says you're closed, you have a guy kind of guarding the door so that nobody comes in, but the customers that are already in the facility all get served and eventually leave. So just kind of blowing away the entire simulation at a particular time isn't going to work. What you want to do is you want to stop the arrivals, but then keep the other events going. And so just to isolate that, this is what this little snippet does. So up here, this is our basic arrival process. Okay, but in addition, what we want to do is we want to stop the arrivals after a certain amount of time. So here's our stop time. And it's just, notice that it's not a sequence, it's just a number. So if we open at 9 and close at 7, that would be 10 hours. So if our time is in hours, the idea is that now the run event is going to schedule a stop, or we can call it whatever we want, but let's just call it stop. And when that's so these arrivals are just kind of keep happening. And then when the stop event occurs, notice it's going to cancel the next arrival. Now, if remember in the computer assignment, you notice that at no time was there more than one arrival on the event list. So, so when stop occurs, cancels the next arrival, no more arrivals will happen. Okay.
When you do that, Arnie, would TS immediately go on to the event list?
Well, TS is a time.
Well, so would stop go on to the event list at time TS?
Yes.
Okay.
So that's what this means. That's what this means. In other words, okay. When one event has an arrow, a scheduling arrow to another event, then it schedules that. So at time 0, you'll have an arrival, and then you'll have this stop event. And let me show you that. Okay, so here is that put into, let's see, where is it? Yeah, I call it a stopped arrival process. And what I did was, and I'll kind of go into this in a little bit more depth later, but basically I'm extending arrival process because I'm lazy. So I'm just going to use all the arrival stuff that the arrival process has, and then just add some more stuff. And the one thing I'm going to add is a stop time, which actually I should be private. I'll have to fix that. Yeah, so stop time is a parameter. And in addition, we have the inter-arrival time generator. So when we're subclassing one of these SimEntity base guys, again, we always have the 0 argument constructor. That's something that we may or may not get to. The 0 argument constructor is useful when we are instantiating these from an external data source. But when we're just writing main methods, it's usually more convenient to just have this so-called master constructor. So we have our inter-arrival time generator, which is required by our arrival process. Again, notice I called it super. So what that does is that calls the superclass of the arrival process, and then I set the stop time. Okay, so stop time is right here. So here's the setter. Now here's the thing is that, and we'll be encountering this a lot. The stop time needs to be at least bigger than or equal to 0. We can make it 0, although that won't be terribly interesting. But if we try to pass a negative value, and unfortunately Java doesn't have a type that says non-negative number, it doesn't have that. So we need to protect it by saying, if we give it a negative number, we're going to say, nah. Why? Because if we try to schedule with a negative number, we're trying to move the time backwards. And until such time as there are actual time machines, then we don't kind of do that. Okay, so here's where things actually happen. Here's the run event. Okay, so in this particular case, we need, and we'll get into this more later. I actually have to directly call the superclass run event because I need that. We don't always do that, but in this particular case, I do. This is the one and only time that we directly call our do methods. Okay, so here's the wait delay. I wait delay stop, and then here's the stop. The call in SimKit for a canceling edge is called interrupt. Why did I call it interrupt? Because, well, back when that seemed like a good idea at the time, but I would name it something else if I were writing it today. That doesn't matter. So this is all that's added. Okay, so if we run, so here's how we can set this up. So again, we need an inter-arrival time generator. And now instead of exponential, I'm gonna use a uniform between 2.1 and 5.2. Where did those numbers come from? I just made them up. And let's stop it. Misspelled cancel. Okay, here's our stopped arrival process, and I need to pass it the inter-arrival time generator and the stop time. Why? Because that's what the constructor says. Okay, so this all should be familiar from the first computer assignment. I have the simple property dumper that's going to just listen and just sort of see what happens. Printing the arrival process, the toString will print the parameters, and that's important because it verifies that the parameters are in fact happening. So when I run this, okay, so let's take a look at what happens here. So first of all, this is the toString, which is automatically generated from the SimEntity based superclass. So verify that my stop time is going to be 20, My inter-arrival time generator is uniform 2.1 to 5.2. Okay, check. So now notice that at time 0, there was one run event on the event list. And when it gets executed, it schedules an arrival and it schedules the stop. And notice, unlike the when we had the event list stop things, here it's actually the stopped arrival process that's scheduling this stop. And so as we see, we have arrival, 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 and then finally stop bubbles to the top. And then when stop happens, the event list empties out. Because why? Because all that stop did was it interrupted the next arrival event. So here, after this arrival, notice we have a stop event, we have an arrival event occurring at time 23, but then when stop occurs, it cancels this arrival. Okay, so that's how to use a canceling edge, and that's how, that's how to use.
Arnie,
Yeah.
When you have that printout, when it says event list 0, that's just saying that's the first event list?
Yes, actually the
Could you just go through that real quick? Because some of those numbers
Yeah.
are a little confusing.
Yeah, one of the features of SimKit is that you can actually have multiple event lists, and 0 is just the first one because it's 0-based indexing. You can actually have as many as your RAM will provide. Let's see. Well, remind me at some time I can show you how we can create new event lists and have different stuff going. It turns out if we want to run multi-threaded, then that's kind of the way to do it. But for now, it's not really germane to what we're talking about. Okay, so that's the canceling edge. All right, the next feature are parameters on the edges. And the idea here is that, well, you notice that there's a one-to-one correspondence between events and methods. So, and since methods can have arguments, then it makes sense that an event can have arguments. So here's an event, and the event has event B has an argument and called it K, just as a generic term. An event can have as many can have as many or as few arguments as you like, just like with a method. Although it's generally best to not have any more than 2. One or 2 at the most is generally recommended, but you can have as many as you want. So here's the canonical form. So here's our event A. Again, scheduling edge, we have a delay. Here's the delay. We have the Boolean condition. And then here, just like when we invoke a method, we need to pass it a parameter. So here we have an argument K, and here we have a parameter. Now this parameter, notice I say it's an expression. So the expression can be anything which evaluates to a value which is consistent with the argument, just like if you were calling a method. Now, unlike sort of plain Java, when we invoke a method, the compiler will stop us if we try to invoke a method with the wrong argument, with the type. In other words, if K is a string and I try to invoke it with an integer, then if I'm doing it directly, the compiler will say, nuh-uh. Here, since we're not invoking the event methods, the do methods directly, we're invoking them indirectly through the wait delay call. there's no compiler check. So it's a little bit more, we're kind of, we're taking away the compiler net on this. So in other words, if, let's say, the argument here is an integer, and I do a wait delay, but I call it with a double, then it's not going to work. And so what SimKit does is it's just going to ignore it and say, okay, it's not a match. But again, the way that it works is when A occurs, this expression gets evaluated. And then if the condition is true, actually, if the way you usually want to do it, if the condition is true, then you evaluate the expression, schedule event B with this parameter as its argument, t time units later. Okay, so here's this, one of the simplest examples of this is a for loop. Now the thing is, in pure event list, event graph methodology, there's no such, the for loop doesn't exist. In other words, state transitions are just basic assignments. They are not, you can't put a for loop into a strict event graph. However, this is how you write a for loop, or this is one of the ways. And here, this kind of init term is something which turns out to be, it's just something that I use. It's an arbitrary name. Okay, so let's unpack this a little bit. Well, first of all, here all the delays are 0. So, and if a delay is 0, then you just leave it off, because that's the default. Now, run schedules init at time 0, passing it the argument 0. Okay, then when init occurs, it's the first init event is going to have the value of I equal to 0. Then what does init do? It schedules itself, and it passes I plus 1. So it takes the value that it had, adds 1 to it, and passes that to the next occurrence. And it does it only if we're less than m minus 1, where m is just the number of times we want to do it. Okay, so again, you start off, we pass a 0, and then every time init occurs, we're going to schedule another one with 1 more until it's actually equal to m minus 2. Or when I becomes equal to m minus 1, then we don't do it. Okay, so let's look at how that looks code-wise. Okay, so here in the code is there's a class called for loop, and should be private again.
I can't see the code, sir.
You can't see it. Okay, let's. It would help if I shared it. There. Okay. Okay. Yeah. Yeah. One thing this is an unfortunate NetBeans things. Like in NetBeans, when you refactor something and encapsulate the fields, you have to watch out for this field's visibility. And so if you just leave it private, it makes it private. If you leave it protected, then it changes it to protected. So I commented on some of yours on that, and it wasn't your fault. It was probably NetBeans' fault. But just something to watch for. Okay. So the parameter is the number of iterations. All right. And again, that had better be positive. Okay, so if it's less than 0 or equal to 0, then I'm going to throw an illegal argument exception. All right, so let's look at here's the run event. Now the run event, I've added something in here that I'm going to talk about later. Okay, so the run schedules init with a delay of 0. And then here's where another optional argument is, this is a priority. I'm going to talk about priorities later here for a variety of reasons. I want to make this a higher priority than normal. So just remember, don't worry about this for the time being, but here's the argument. The last argument in a call to wait delay is going to be the parameter that it gets passed. And here's the init event. Here its argument is an integer I. So here's the test. If I is less than the number of iterations minus 1, then I schedule another init with a delay of 0 in higher priority, but passing it I plus 1. So what does that look like? Okay, so let's do it for 5 iterations. So I'm going to instantiate my for loop with that many iterations. Now, in this particular case, I don't need to stop the simulation, because this is going to run 5 times and then stop. So I don't need to stop at time. I do want to verbose. There aren't any state variables, so there's nothing to really listen for. Okay, so when I run this, okay, so again, you always want to print your guy. You always want to print these just to verify that, in fact, the parameters you thought were giving it, you were giving it. So number of iterations. Now I want to watch for the init events. So here I schedule the init event, and then here in the curly braces is the argument. So run scheduled init with an argument of 0. And now here's the init event occurring with an argument of 0. And then it schedules an init event with an argument of 1, I plus 1. Last I checked, 0 plus 1 is 1. Then what's the next thing? The next is the init with an argument of 1. It schedules, remember, M is 5. And so 5 minus 1 is 4. So is 1 less than 4? True. So we schedule 1 with 2. Then init occurs with an argument of 2. Is 2 less than 4? Yes. So it schedules 1 with 3. Okay, so 3 is 3 less than 4? Yes. So it schedules 1 with 4. And then finally, init with an argument of 4 occurs. Is 4 less than 4? No, it does not schedule anything. We're out of events, and so now the simulation ends. So one thing to notice on here is these little numbers in brackets. So can you see what those are? The number in brackets, as the events occur, is just a count of, this is how many times this event has occurred. So the run event has occurred once here. And then the init event has occurred 1, 2, 3, 4, 5 times. So that's what we wanted. Okay, so, and that's what was implemented. That's this event graph I have right here was what that code implemented. With the one exception that what was not shown was those high priorities, and that's represented by these little circles like this. We'll talk about that in a little bit. That's something which sometimes happens that we have to worry about a little bit, but for now we can just kind of not so much. So one example of this is that if we wanted to say schedule event A have M instances of event A on the event list at time 0, then we could simply schedule them from the init event like this. And that's something which is going to come up a little bit when we, well, in at least one of the models that I'm going to ask you to formulate. You're going to need to do something like that. Okay, so now as a concrete example of using an argument on an event is this periodic review inventory model. Is anybody familiar with this term, or have you studied any inventory models at all? I'm hearing crickets, so I guess nobody yet. No? Okay. All right, well then, so this is your first one. Okay, so the idea here is that you have an items inventory and you only check it periodically. This is called a periodic review. Why do we do this? You may be asking, like, why don't we just sort of constantly monitor it? Well, think about how many parts the Navy, well, I've been doing work for the Navy on this. They literally have hundreds of thousands of parts. And so keeping track of each one, even with fairly fancy computer models, is not something that you always want to do for everything. For expensive items, yes, you do. But for this is a thing, and this is something which also occurs with companies. The idea is you only sort of check the inventory level periodically. The opposite of this is something called a continuous review model, but that's not something we're going to be looking at immediately. But here's kind of the key thing: is it's a sometimes called a little s big S model. So the idea is that when your inventory level falls below a certain amount, and that's called little s, and this is the terminology. It's not the greatest, but that's what they call it. An order is placed that would bring it up to big S if it arrived immediately. In other words, instead of ordering a fixed amount each time, when you check your level and it falls below a certain amount, you order all the way up to big S. We'll see an example of that. One way to kind of think of that is when you fill your car up at the gas station. So your little s might be, so let's say you have a rule that when you hit a quarter of a tank, then at the next gas station, you're going to fill it up. Okay, so typically then you're going to have less than a quarter of a tank. How much less? It's going to vary. But then when you fill it up, you bring it all the way up to big S. In other words, the amount that you put in is not a fixed quantity. And that's why this example is being used to show the argument. This is where the argument on the event is going to be key. The trick, though, is that unlike the gas, when you place an order for something, it only arrives after a certain amount of lead time. And the lead time is the time between when you order it and the time when it shows up. And that can be a very long time. In some of the Navy items, it literally can be years between when they order something and when it actually shows up. And I was a little floored by that, but I think there's probably a good reason. Okay, so the idea is that, okay, for this model, our customers are going to arrive at various intervals, and each customer is going to require a random number of items. And then if we're out of them, then we're going to back order them. In other words, we have captive customers. If they don't, if we don't have it, then and they want it, we're going to back order it, which means we can't give it to them right now, but then the next time they come in, then we'll get it. I'm sure you've all had situations more or less like this. Now, so we assume that you want that thing. It might be due to brand loyalty. It might be due because this is the only game in town. It might be due that there's no viable alternative and you got to have that thing. Okay, but that's the rule for this. If we don't, there's a so-called lost sales thing where if we're out, then maybe there's a certain probability that they'll say, well, never mind, I'll go down the street and get it from somewhere else. But that's not the situation. So for example, like around here on the peninsula here, there's a Home Depot and there used to be an Orchard Supply. A couple years ago, Orchard Supply went out of business. And so now pretty much Home Depot for those in my area is pretty much the only game in town. So kind of stuck. Okay, so here's kind of a diagram just to kind of illustrate this. So here's our so-called reorder point. And then this is the order up to. What the red lines are kind of showing in actuality, these are going to be kind of more jagged because it's random. So here's our inventory position. So here we start with this amount, and as the demands come in, we decrease and decrease and decrease. And then here's what happens. Here, these are the times when we review. So we review at this point. And at this point, we're above our trigger point, so we don't do anything. But then the second time we review right here, so when we review at this point, we say, we're below our order, our reorder point. And so we're going to place an order for this amount right now. Okay. The problem is that notice that this is a dotted line. The time between we place the order and the order arrives, this is our lead time. This time here is our lead time. So even though we have it on, it's coming, but it hasn't come yet. And our customers are still coming in. Now, as they come in, notice that here we still have items to give them. So this is 0. But then when we hit here, these guys have to be back ordered. So all this demand here, we can fill immediately. And then when we hit this part, these guys have got to be back ordered. Then all of a sudden, our order that we placed back here, it shows up. And now we have these items. And so we fill our back orders, and then it keeps going. And then notice here are our reviews here at these points. And then here's another place where we've hit our reorder point. We order up to here. This is how much we order. So it's a different quantity. The demands continue, and then sometime later our order shows up, and then so that's how the model works. So let's formulate this as an event graph model. I'm seeing a question. Yeah, you're absolutely right. Or even, yeah, typically, for a lot of these items, the manufacturers don't sort of sit around waiting to have them there. They have their production facilities tooled to make particular things, and then all of a sudden they get, when they get that order, they have to typically retool their production facility to make these new things. And then in the meantime, they're still making stuff for other people, so they have to kind of finish things and do other stuff. So yeah, it takes a long time. So there could be a long time between this. So, but we're modeling it now. So this is, again, a periodic review, little s, big S model is what it is. So what are these parameters? So we have the time between demands. That's kind of like an arrival process. But then on top of that, every demand had a certain number of items that were demanded. Okay, so that's another sequence of random variables. Now our lead times are typically random as well. So we're going to have that as another parameter. The time between reviews, now that's something where that's something that we can control. So in a way that's a parameter, but these guys are a bit out of our control. We don't know, that's completely exogenous. The time between reviews, that's something we can control a little bit. And here's another, we're going to start with a certain amount. That's going to be our initial inventory. We're going to assume everything else is 0 for the time being. And then our decision, in a way, these are our policy. That is our trigger quantity and our order up to amount. Those are, again, those are going to be fixed quantities that we're going to have for the model, but those are also things we can fiddle with. So let's look at our state variables. Our state variables are the amount on hand, which is initially going to be our initial amount, the amount that's back ordered, which is we're going to initialize it to 0. T is going to be the total amount that we have on order. In other words, we don't want to be kind of over ordering. So if I hit a review point, and even though the amount that I have on hand is below the reorder point, if I have stuff coming in, I'm not going to order more. And then just for bookkeeping, I want to keep track of what's the total number of items that I order throughout the whole thing and the total number of orders that I place. Okay, why worry about this? Well, because sometimes, basically every time I place an order, it's going to cost me a certain amount. And then the total number of items that I've ordered, again, that's going to cost me a certain amount as well. And the thing to recognize is that the relationship between the amount on hand and my back orders is that one of those is going to be 0. In other words, if I have items in stock, I'm not going to have any back order because I would have filled them. Or if I have items on back order, then I shouldn't have any in stock. Okay, and this is what the event graph model looks like. All right, so here are our demands, and then here are our reviews. So remember, the demands are not going to cause us to do anything. It's the reviews that are going to cause the orders. So, okay, here's our run event. We initialize all of our state variables just as we've defined them. So when we define our state variables, we can always immediately write our run event to prevent sort of the blank page-itis, as it were. All right, so let's look at the demands. The demands, this is like an arrival process, only I'm going to call it demand because it's not exactly like an arrival. Remember, an arrival only incremented the number in queue by 1, but here, okay, so remember D is a random variable that is how many are demanded. And so to figure out whether this is just sort of a way to identify whether or not I can, the heck, it's not letting me. Okay, this is a way that, okay, the net amount that I have on hand versus back order is amount on hand minus the back order minus the new demand. And that's either positive or negative. If that's positive, then the amount I have on hand is the maximum of that value and 0. So whether if it's positive, then it's going to be how much I have. If it's less than 0, it's going to be 0. And the number I have on back order is going to be the maximum of minus that net value and 0. So if net is positive, that means I have items on hand. Minus net is negative. That means that the maximum of a negative number in 0 is 0. So after all this, I either have items on hand or in back order. So, but here's the kind of the crux of the thing. Now here, my review, interestingly, has no state transitions, but it's just an event whose only purpose is to figure out whether or not it can place an order. So and it's going to occur periodically with my time between reviews. Remember that for this model, that's a constant value. Okay, so let's look at the condition. So here's the condition. I have a certain amount on hand, a certain amount of back order, and a certain amount on order. If that total is less than my reorder point, then I'm going to place an order. And I want to place an order for the amount between how much I have there net and this big S. And what is that amount? It's S minus I plus B minus T. In other words, it's my order up to amount minus what I have on hand, plus the amount on back order, minus the amount that's on order. And I pass that, okay, notice, remember I said expression, that's an expression. But for an event, the event is an argument, and the argument is only a single value. So what this says is that if in my review, if I meet this condition, I will place it, I will schedule place order immediately with time 0, passing it this value that I've computed. Now the place order event says, okay, so I've been told to place an order for this amount. So I don't have to do this calculation again. Because now I have a state transition. The amount on order is going to be incremented by that amount. And the total number of items that I've ordered is going to be incremented by that amount. And the number of orders that I place is going to be incremented by 1. And after that state transition, I want to schedule the arrival of the order. Okay, I have my lead time, and I'm going to pass as an argument, as a parameter, this amount that I was scheduled to place after a lead time. And when the order arrives, now I have that much less on order, and my net is again going to be my amount on hand minus back orders plus the amount that I received. And then I do the same translation here. So if my net is positive, then that's how many I have on hand. And if net is positive, then minus net is negative. That means that my back order is 0. On the other hand, if the net is negative, even after receiving the order, I could still be in a back order position. That means that net is going to be negative. And so the amount on hand I have is going to be 0 because negative is less than 0. But a negative of a negative is a positive. And so the maximum of that is going to be the amount that I'm short.
Sir, could you help me understand and explain the difference between T and N?
Okay, T is the amount that I have. In fact, if you look carefully at the state transitions, you can see the difference. T is going up and down. That's the total amount on order at any point in time. N is always going up. So T is the amount on order at any given time. So when I place the order, I've increased it, but when the order arrived, I've decreased it. N is the total amount that I've ordered through the whole simulation. And that just keeps going up.